Thank you very much indeed. Thanks for inviting us back again. I'd like to talk about atmospheric chemistry in numerical models, and in particular, how we include it and how we solve the necessary equations. So I want to look a little bit at the theory of chemistry in models, and then I want to look at how things are done within UKCA. So I'll start off with, you have this fantastic chemical scheme that you'd like to include in a model. How do we go about doing that? An example here of oxidation of a couple of biogenic hydrocarbons, alpha pinene and beta pinene. If you start looking at the chemistry of these things, it very quickly gets complicated. They react with a variety of things in the atmosphere. They form numerous products. Those products go on to react with other chemicals and form yet more products. We like to include this scheme in a model. How do we get from there to understanding how the concentrations vary with time? Initially, a bit tricky. Chemistry in a model, how do we deal with it? But if you stop and think about it, it's actually not terribly different from atmospheric advection you've just been hearing about. For advective processes, we're looking at conservation of mass, and we're thinking about how we move mass of a particular tracer from one location to another location within a given time step. Well, for chemistry, we're doing something very similar, except we're moving mass from one chemical species to another chemical species within that time step. So same kind of process is involved, and we've still got that conservation of mass as our underlying foundation. Okay, so so instead of understanding the chemistry, we need to understand how things, understand the chemical rates rather than the advective rates for transport. So how do we deal with chemical rates? And for that, we need a little bit of physical chemistry. So apologies if some of you already have got significant chemistry, but there's a little reminder of some physical chemistry here. If we have a certain number of molecules of reactant A and B molecules of reactant B, we form some products C and D. Usually these little a's, little b's, c's and d's are actually a 1. So we've just got one molecule of A and B reacting to form products C and D. We describe the rate based on this expression here. Basically, the rate is dependent on the concentration of reactant A and the concentration of reactant B and some constant of proportionality, this rate constant. There's some physical foundation for this rate constant underneath. Is usually defined, usually measured kind of observationally. We do chemical kinetic experiments in the lab to define what these rate coefficients are. But typically it depends upon the activation energy of a particular reaction. Okay, this little E term here. It depends on temperature, and there's some pre-exponential factor, some Arrhenius factor at the end here. We don't have to worry about where the details are, but these are characteristic constants, rate constants for a particular reaction. Okay, they depend on temperature, may depend on other things, but we need to know what those are in order to understand what the rate is. And for the rate, we're looking at the rate of formation of product C, the same as equal in this particular case to the rate of removal of reactant A. Okay, and assuming we have one molecule going to one molecule, this term here is just 1. So the rate of loss of the reactants is equal to the rate of formation of the products. And if we look at an example of this in the atmosphere, particularly important example here, nitrogen oxide reacting with ozone to form nitrogen dioxide and oxygen. Then we can express the rate of loss of NO, the rate of loss of this reactant, as the concentration of NO times the concentration of ozone, or the concentration of these two reactants, times the rate constant. And there's a minus sign here, of course, because this is a loss of the reactant, NO. Now, if you look at this equation, you'll see it's a differential equation. We involve the concentration of NO is involved in the expression which defines its rate. So in other words, if we want to solve this, we have to integrate. All right, so it's a differential equations. Now, chemistry in the atmosphere, lots of different species involved, lots of species coupled with each other, so we have to solve lots of equations simultaneously. Here's an example of a little chemical system in the atmosphere, reactant A forming B, and then B can either go on to form a product C, or it can collapse back and form A again. Little chemical network here, and we can write out the expressions for the chemical rates of each of these individual chemical traces in the atmosphere. For example, the rate of change of reactant A is dependent on its loss here, the reaction 1, plus its reformation again from B through reaction 2. And equally, B depends on its formation from A and its loss through either reaction 2 or 3 to form A or C. And similarly for product C. So we have to solve these 3 differential equations simultaneously. So when we're talking about chemical solvers in atmospheric models, we're looking at simultaneous solution of ordinary differential equations, which are coupled. Right? Expect to get something looking a little bit like this in this case. The reactant A drops off, B increases and then decreases again, and eventually we all end up forming this final product, C in this case. So how do we solve ordinary differential equations? Well, usually it's quite simple. We just simply integrate them. Let's look at a very simple example here. Reactant that basically falls apart to form some product B. All right? Simple first order loss. Example might be thermal decomposition of peroxyacetyl nitrate or something in the atmosphere. Example might also be for radioactive decay in the atmosphere. Fixed half-life, single rate, which depends on the concentration of the reactant itself. So we can write down the rate of loss of this particular reactant A. Equals minus because it's a loss, K the rate constant, and A the concentration of the reactant. And we can integrate that analytically. It's very straightforward. Simply rearrange this. So it's the integral of 1 over A dA, and the integral on this side of K is a constant, 1 dt. So we come out with a log term on this side. And if you follow through with the maths here, you end up with the concentration of this product at time t, this reactant at time t is equal to the initial concentration times its exponential term. This exponential depends on its rate constant. Okay? So what you get is a decay of the species, an exponential decay. Okay? With the rate of decay depending on the rate constant itself. So it's a very simple example. So if you want to work out what the concentration of the thing is next, you simply have to use this expression here, and it'll tell you. It tells you the concentration at any particular time. Now, of course, in the atmosphere, things aren't quite as simple as this. We have lots of systems, lots of chemical equations coupled together, and in general, you can't solve these things analytically. So we're going to have to try and use a different method for solving our simultaneous equations. Typical simple approach is the Euler method. So very simple to apply. We have the chemical rate equation here. This is our rate of loss of A. Okay. What we're doing is we're simply expanding that and saying, well, for a small change in A is equal to minus the rate constant times the concentration at that point times the time step. All right. Now the simplest assumption is let's just take our initial concentration, calculate what the rate of change is at that point, okay, and plug it into this equation to come out with a new point down here. We take a fairly small step in time. So evaluate the gradient at the current time, use that to calculate how much it's going to change over that period of time, and then you get your new concentration at the end of the time step. And we'll take fairly small time steps to keep things stable. Okay, and we simply repeat that process. You need to keep the time steps really quite short, otherwise the errors start to build up. I've kind of exaggerated that here, but if you follow through time steps, step by step by step, you can kind of follow the shape of the decay. All right, so quite a simple technique. However, there are problems with this type of approach. It's good for some systems, but if you've got situations where rates are changing very quickly, you may be forced to take very, very small time steps, and that will then, of course, put quite a large computational burden on the solution. The main problems with stability. If you've got rapid changes in some of these reactions in the atmosphere occurring in quite short time scales, if your time steps are too long, you can overshoot. You may get oscillations occurring. You may have divergence, so you don't converge on a solution. Take slightly smaller time steps, you see you may get oscillations. You may still converge on a solution, but you may not. So it depends a little bit on the problem that you're solving, whether this kind of simple Euler step is going to work or not. You can immediately see some kind of improvements that you might make to this type of solution, rather than evaluating the rate at this point here. You might prefer to aim for some kind of midpoint here. So what you could do is take the initial concentration, take the concentration at the end of the step, just use this simple Euler method, find a point halfway through, work out what the gradient is at that point, and then use that point to evaluate what this concentration at the end of the step is. That's called a midpoint method. So you may take there are a number of improvements you can make, but they all involve more calculation. So you've got to trade that off against the small steps that you need to make to actually fit that proper solution for how the concentration changes with time. So that's one approach. That's an explicit approach. So what we're doing is we're using the state of the current state of the system to define the future state, right? So the advantage is a very simple little system. So the concentration at the time t is equal to the concentration at time t plus 1 is equal to, as a function of the concentration at time t. Very simple to evaluate, easy to implement, but it starts to become a problem if we need very small time steps. Okay, what's called a stiff system. We have a very wide range of different time scales involved in the chemical system that we're looking at. And one way around this is to use an implicit method, and that we're looking at the state of the system at the end of the time step at the same time as the state at the current state of the system. So effectively, we're looking at some function which is something which is a function of both the current state and the future state, and we're trying to minimize this close to zero. So this has a disadvantage that you're going to have extra calculations to solve. Okay, we have to solve this equation. It's a little bit more complicated to deal with than this simple one step that we have for the explicit approaches. But the advantage is you can use much longer time steps. You're no longer limited by having to take very small steps in time. All right. So it might take 5 times longer to solve this than it does to solve this one. But if you can use time steps which are more than 5 times longer, then this way is going to be computationally preferable. Okay, but the actual best approach depends on the chemical system that you're looking at. Right, this applies to many different. You could apply these to many different types of chemical system. Generally, in the atmosphere, we have a very wide range of different timescales involved, and we tend to prefer these implicit schemes. Okay, they tend to be generally more stable and more computationally beneficial. So how do things work in UKCA? Okay, well, what we do is tend to use one of these schemes is called a backward Euler scheme. So it's an implicit method. Okay, we look at the current state of the system. Here's our concentration at time 0. Okay, we take a simple Euler step forward. We work out what the concentration should be at the end of the time step. Okay, based on a simple assessment of the gradient at that initial time. But we don't stop there. We keep going. We reevaluate it. We put this back into the equation again, and we calculate what the gradient is at this point here, and then we use that to calculate a second guess at what the concentration at the end of the time step is. So whereas in this particular case we overshot, if you like, in this case we undershoot. We take this point here, we put it back in the equation, we calculate what the gradient is again, we put that back in the equation again, we come out with a third guess. Okay, and we need to iterate step by step by step, and each time we get closer to a true solution. When we've finally reached some level of some tolerance, we actually end up with a value which is much closer to the actual true solution, the red line there, than our guess there. So you see, it's quite a simple formulation, but it involves some form of iteration, computationally more demanding. But the accuracy is, of course, far better. Okay, so we typically, as I said, set this expression. We start off by using the current current concentration and reevaluate. So with some form of iterative procedure, iterative solution. So it tends to produce a very stable approach, and means we can take quite large time steps. We're not limited to small time steps anymore. Okay. So this is actually, we tend to rearrange this equation. It forms in this form here. I'll come back to this again a little bit later when we look at how things are actually implemented in UKCA. So computationally much more demanding than the Euler approach, but more accurate, and you can take nice large time steps. It tends to work very well for atmospheric chemistry systems, whether you're looking at air quality type chemistry or whether you're looking at kind of global atmospheric, troposphere, stratosphere chemistry. How does the iteration work? Well, relatively straightforward. It's basically a Newton approach. We take a first guess of what the concentration should be. So initially, the first guess was the concentration at the present time. Okay, we evaluate the rate of change, the chemical rate, at that particular concentration. Okay, that could give us a second guess. Okay, when we use that second guess, calculate the rate at that point. That'll give us a third guess, and so we go on. We iterate. Okay, and eventually, if we're looking at where the gradient crosses zero, we're looking at minimization. We're looking at where we cross that x-axis. We zoom in effectively, focus in. We eventually get to the crossing point. Okay, that's what we're looking for. We're looking for the point at which this point here. At that point there, then we know we've got we can derive what the rate of change is for the chemical species. Okay, so it's a little bit tedious. If there's an issue of making sure that you have a reasonably good first guess. This complex function here, the rate of change of that species, depending on the concentration, may be quite complex. If you choose a value which is too far out to start with, there may be problems. But as long as your first guess is reasonably close, not too far away from the solution, then using this approach, you can zoom in quite quickly on the solution. There are lots of other integration methods out there. There is a whole, obviously, field of numerical methods that I encourage you to have a look in if you're interested in digging into this type of topic. There are some others you might meet. Adams-Bashforth is a very simple little explicit scheme. It's an example of a two-step scheme. So the first step here is just the same as an Euler step. The concentration at the end of the time step is just the concentration at the beginning of the time step minus the change which is evaluated at the beginning of the time step. But then we use this first guess here in this little expression here, which takes a little bit of the first guess, this one here, plus a little bit of the second guess and kind of combines them. Right? So it's a kind of two-step process. Clearly takes about twice as long to do as the Euler step, but it's a rather better, it's a rather closer solution. So again, still very simple. A little bit too simple for the types of chemical schemes we have in atmospheric models, but you do see this type of approach used sometimes. In fact, the Cambridge 2D model, stratospheric model, used to use this kind of approach. Very simple integration scheme, quite easy to implement. You may come across these Runge-Kutta techniques. These may be implicit or explicit, and they use some, again, they're iterative, but they use some kind of parameterized, some kind of expression which balances the rate evaluated at the beginning of the step with that at the end. Okay. Some of the most accurate methods you meet are gear methods. These are backward differentiation formulae. So they use some kind of expression for arriving at what the concentration at the end of the step is, using some formulae, but they're also iterative. And you'll meet these, for example, this kind of sparse vectorized ordinary differential equation solver here, SVODE, the SMV gear package. Again, these are used by models such as GEOS Chem. Rosenrock solvers are another family of chemical solvers. Again, a little bit similar, multi-step methods. You might be familiar with these if you've looked at KPP, kinetic preprocessor. That's a way that some models include chemistry in their atmospheric models. KPP is used in WRF-Chem, regional model, and a variety of other models available in the community. So there's a whole variety of different integration methods here that one could use. Let's say that for UKCA, we use the backward Euler approach. It's both efficient for the chemical systems we're looking at, reasonably nicely optimized. One problem we have in chemical systems is stiffness. And this is basically when you actually have forced to take really small time steps. You don't really want to have to do so. Some examples where this might be is when some species decay much more rapidly than others. We might have chemical traces in the atmosphere with lifetimes of of 10 years, we might have lifetimes go down to a fraction of a microsecond. So we're talking about 9, 10 orders of magnitude at least in terms of rates of change of the different traces we want to deal with. So these are quite stiff systems to deal with. So that if we want to do those in an explicit, we want to solve those in an explicit technique, through an explicit method, we'd have to use really, really short time steps. That's going to kill us. So it's basically situations where the step length is constrained by stability rather than accuracy. If we take time steps which are too long, we're going to get oscillations, and our chemistry is not going to converge. And also a problem when we have strong coupling between different species, when small changes to one species make significant changes to another, but that feeds back on the first one again. So we often have situations where there's strong relationships between chemical species in the atmosphere, rapid interconversion from one species to another. Right. But we can alter the stiffness of a system by putting species in steady state, or by taking what's called a family approach, putting things in chemical families. So let me show you some examples of these. Here's an example of steady state. Let's say we have reactant A breaking down to form reactant, or forming this tracer B, which breaks down to form C. Little network like this, you often have this kind of system in the chemical environments. Let's say reactant 2, the reaction 2 here is much faster than reaction 1. So basically, as soon as we form B, it goes on to form C. Okay, it's removed as soon as it's formed. So what we're saying is that if there's no other reactions involved, then we can consider B in steady state. It's in equilibrium. As soon as it's formed, it's removed. Okay, the rate of formation of B, product of A times reaction rate 1, and the loss is reaction 2. Basically, that equals 0, because basically we're not changing. As soon as it's formed, it goes on to form C. So effectively, we can rearrange this equation here, and B is then simply a function of reactant A, with proportionality dependent on the ratio of the two reaction rates. Okay, so effectively, we can take B out of the chemistry completely, and we can think about A going straight to form C. The formation rate of C no longer depends on B, it really just depends on A, because this first reaction is the rate limiting step. All right? So we don't need to solve for B, we can drop B from our chemistry. We don't have to worry about K2 either, because it's a very fast reaction. So we can simply treat this as A going to reaction rate 1 to form C. Get rid of the really short-lived species in the middle. And that'll reduce the stiffness of the chemical system that we're looking at. Another example is that of chemical families. Here's an important example from stratosphere, the Chapman cycle for atmospheric ozone. Okay, we have oxygen here, photolyzing to form an oxygen atom. Okay, that reacts very quickly picks up oxygen to form ozone, and ozone decays very rapidly to form oxygen. And ultimately, on some longer time scales, we get reaction of these things to form oxygen again. But reaction 1 and reaction 4 are both relatively slow compared with reactions 2 and 3. This interconversion of atomic oxygen and ozone is really very, very rapid in the atmosphere. So if you want to solve for all these things together, it's quite complicated. Not as I say complicated, but it's a much stiffer system. Much greater rates a variety of rates of change are involved. So what we can do is, if we consider these two things together, just consider these as odd oxygen, one single species. Okay? Then all we have is the formation of odd oxygen in reaction 1 and the loss of odd oxygen in reaction 2. And we can solve our chemistry just like that. Okay? And when we get to the end of it, we can derive atomic oxygen and ozone from OX based on the ratio of these two reactions, K2 and K3. Okay? So effectively, we don't have to worry about the fact that these are very, very fast reactions, meaning these two species theoretically have very short lifetimes. All right? So that's another way of simplifying the chemical scheme in our model. Treating families, that reduces the really short-lived species, so we don't have to worry about those. So let's look at a real example. Here's the oxidation scheme for methane in the atmosphere. All right? It's got quite a long lifetime. It's quite difficult to abstract a hydrogen from methane. That's what we have to do if we want to get it to react. We have to we have reaction with the hydroxyl radical, OH. And OH in fact, it takes the hydrogen off methane. Very slow reaction. Lifetime of methane is about 10 years in the atmosphere. It's difficult to abstract the hydrogen from methane. When we do, we get this methyl radical here. And this radical is extremely reactive. Okay, lifetime of milliseconds. Bumps into an oxygen, will form this peroxy radical here. Methyl peroxy radical. Again, that can go on and react in the atmosphere, a whole variety of different ways. I've just given you one example here. It can react with nitrogen oxide to abstract an oxygen to form this methoxy radical. The methoxy radical is also fairly short-lived, lifetime of about a second or so to form, and that will react with oxygen to form formaldehyde, methanol in the atmosphere. And methanol can then go on to react with OH or photolyze to form carbon dioxide and H atoms, radicals. Okay, these H atoms, radicals, quickly pick up oxygen to form HO2. Again, very short-lived. And the carbon monoxide reacts with OH to form carbon dioxide. So you've got a full chemical scheme here, whole series of different steps. The slowest one is the first one, but once we've started this, the rest of it goes fairly rapidly. If you want to include this in our chemical model, what do we need to do? Okay, if you want to include all those things, we're going to end up with a very stiff system, because then we have wide range of different timescales involved. But we can simplify it quite substantially, okay, using concepts of steady state and families. We can identify the reactants which are very short-lived. So, for example, this methyl radical here. We don't really care about this too much in our model. We know that it picks up oxygen pretty much instantaneously to form the peroxy radical. So we can actually drop this species and drop this whole reaction. Okay, we can just have methane and OH going straight on to form this peroxy radical plus water. Okay. Equally, the peroxy radical forms this oxy radical, and this one again is very short-lived. We don't need to worry about that. We can skip that. We can drop this step. We can make it go straight on to form formaldehyde. Okay. We may or may not want to keep this one. In most cases in the reaction, we do want to keep this because peroxy radicals are quite important for atmospheric chemistry processes. Okay, and this can actually do a variety of other things. It doesn't always react with NO. Some of them react with each other. Okay, and that's important potentially in many chemical environments in the atmosphere too. So we end up simplifying the chemistry scheme. We're dropping the very short-lived species, we're dropping the reactions associated with those, and we end up with a system which is both simple to solve, fewer traces, and reduced stiffness. Okay, it's beneficial in several different ways. And most of the chemical schemes that we're likely to use in the atmosphere have had this type of approach applied to them to various degrees, depending on how simplified a chemistry we actually want. Okay, how is chemistry implemented within UKCA? Well, for that, we use the ASAD chemistry package. All singing, all dancing. Basically, it's a chemical framework for a model. It's not actually the chemical scheme itself. It's basically contains. It's the kind of package you need in order. You provide the kinetics. You provide your chemistry scheme. You apply it into in ASAD, and ASAD is a framework that it fits into. So ASAD contains a choice of numerical integration packages. I've described some of those. So the backward Euler approach is the standard one, but there are a number of other approaches possible too. The package is independent of the chemistry scheme. So the idea is you can actually change the chemistry relatively straightforwardly without having to get into the nuts and bolts of ASAD itself, the chemical package. And what we're doing is we're solving simultaneous differential equations, as I just described, concentration of whatever y, depending on the chemical production minus the chemical loss. You may have some self-reaction terms in there. They're a little bit more complicated. There's a quadratic term there. We may have emissions in there. We may have deposition involved too. In practice, within UKCA, I don't think we do integrate emissions and deposition together with the chemistry, but the option is there if one wants to. Okay, so we usually just focus on these production and loss terms at the beginning. All right. So within ASAD, we just set up the chemistry. you need to give UKCA a list of chemical species to deal with. The CHCH file tells that in this case it gives a list of what individual traces you're looking at. I think you'll get to play around with this kind of thing in your tutorials. You can define what the chemicals are. You have to define what type of tracer they are. Simple systems here, whether it's a tracer that's considered both the chemistry and the dynamics, whether it's a species that should be treated in steady state, or whether in fact it's a constant. Some things like oxygen and nitrogen in the atmosphere, if we're in the lowest 100 kilometers or so of the atmosphere, we don't care too much about looking at the chemical rates for those, so that we can take those as constant. So that defines what chemical species we need. After that, we need to define what chemical reactions we're going to include in our model. Okay, so again, there are files associated with this. RAT-B for the bimolecular rates, RAT-T for the trimolecular rates. For the bimolecular rates, what we're looking at is we need to think about what the rate constant is. So you need to provide reactant 1, reactant 2, and then there's space for a number of products to be formed from that particular reaction. All right? And then you need to define what the rate constants are, and what we're providing is effectively this pre-exponential term here from best estimates based on lab measurements, and the activation energy here, again, based on best estimates from lab measurements. So what you're doing is you're taking those two terms and you're looking at the temperature from your model, and with the temperature, the gas constant there, the activation energy, and this term here, you can calculate what the rate constant is. Right? So all this is defined in this RAT-B files, or details here in UKCA. Okay. We also have a system so you can actually specify fractions of particular products. There are various reasons you might want to do that. If you're not looking at simple individual elemental reactions, if you combine the number of reactions together, you may get fractions involved, half going one way, half going to a different way, two different sets of products. If you were combining them in a single reaction. Okay. Termomolecular reactions. Some reactions in most reactions in the atmosphere are really quite simple. In the case of two molecules colliding, having some interaction, forming some kind of intermediate, and then breaking apart to form two products which are different from the initial reactants. Okay, that's a simple bimolecular reaction. For trimolecular reactions, there are some reactions where you get this kind of intermediate formed, but you may need a little bit extra energy, or you need some energy removing. So basically whether the reaction goes or not depends on whether that intermediate collides with another molecule in the meantime. If that does happen, we form the products. If it doesn't, then we go back, nothing happens. We back to forming the reactants again. So these are termomolecular reactions. Effectively 3 molecules are involved, 2 reactants and some third molecule. And for that, depends a little bit on, it's a little bit more complicated to implement in these models. It depends on the actual pressure. So in other words, how many molecules there are in a particular area. And generally, these are parameterized based on basically high and low pressure limits. What was the situation if you have a particularly low pressure? So it's effectively a bimolecular reaction. What happens as you increase the density of the air? So the greater chance of a third body being involved. And the parameterization is a little bit more complex here. K0, low pressure, K infinity, parameterized in a similar kind of way. We use this TRO expression here. Okay. Again, you provide the details for this, data for this, within this file for ASAD. Photolysis is a whole different game. Molecules here not reacting with each other, not colliding with each other, but we have the effect of sunlight. The molecule absorbs that light. That may cause the molecule to split up. Okay, that's what initiates most of the chemical processes in the atmosphere. And I believe you'll have a talk tomorrow on photolysis, so I won't go into any further details here. But you need a photolysis scheme in order to provide the photolysis rates that the chemistry is then going to use. So the chemistry needs to know about the rate of removal by photolysis. So within the ASAD framework, let's look at, kind of summarize what happens. Beginning of the model run, we actually need to set up our chemistry. Okay, you tell it what species you want it to use, you tell it what reaction to use, and it will then initialize all the arrays. Okay, and then during the course of the model, as we're going through the various loops, the various time steps, what we need to do when we get to the chemistry time step, we collect the concentrations of each particular tracer. We then calculate what the rate constants are at that particular location. That depends on the temperature and potentially for the pressure for the body for trimolecular reactions. And then based on those concentrations and those rate constants, we work out what the rates are. Okay, we calculate the production and loss rates, and then we integrate those with our chosen integration scheme. Right? Just talked about that before. And then we determine at the end of that, once that's converged, we've got a solution, we determine the new concentrations. And we hand back off to the advection scheme to do its thing. All right? So that's the kind of system. And basically, this happens just once, and then we loop over this multiple times, different time steps during the course of the model run. So if we look at what we actually need, if we're actually coding up ordinary differential equations in our model, this was the traditional way of doing it. You actually write in what the rates of change of each particular reaction are, hardwire it, it's nice and clear with what's what. You know what concentrations you're looking at, concentration of what have we got here, all kinds of bits and pieces here. A good example, the rate constants of particular reactions times the concentration of the reactants themselves, and you can write out what the rates of change of each particular reaction is, and therefore what the production and loss rates for each individual species is. If you've got a simple chemistry, it's dead straightforward. If you start to have a more complex chemical scheme, this gets very very difficult to do. And if you want to start adding reactions, you've got to work out where in this mess of Fortran you're meant to be putting the additional rate constants. And it's very easy to make slight errors, actually miss out a number somewhere. You accidentally hit delete at some point, and you've changed from reaction 92 to reaction rate constant 92 to rate constant 9, and you don't notice it. It's really very difficult to debug. So we've had a couple of innovations. First step is to replace all this with machine-written code. You actually get some chemical pre-processing going on. So we actually write out what the code should look like. That will allow us to kind of automate the system. Means we get away from this errors associated with adding new chemistry. Whenever we want to change the chemistry, we simply have to rerun our preprocessor that will write out what the rates of change are. Okay, provides code looking a little bit like this, for example. Okay, production and loss of each species, one after another. Okay, it's a bit more difficult to work out what's what in the sense that you don't actually writing out, nitrogen dioxide concentrations. You've no idea which of these different Y species in there is nitrogen dioxide. But at the same time, you get away from this issue of errors. So it's really quite easy to write out. You just take that code and plug it straight into your model. This is the way that KPP works, kinetic preprocessor. Whenever you want to change the chemistry, you simply have to rerun the code, and it writes out the rates of change there. Actually, you plug that into your model. With that said, we've gone one stage further than that. We said, let's not bother with code writing at all. Let's lump all these things into arrays. So we have arrays of arrays of arrays. And it means you have a much simpler looking code. You can actually calculate the biomolecular rate constants. You just for each reaction, you just loop over all the different reactions. You take the rate constant times the concentration of reactant 1 times the concentration of reactant 2. Okay, and you plug that into calculating the production and loss rates for each species. You simply loop over production and loss rates for each species and add up the different reactions which are involved. So it's much cleaner code, much less likely to make errors. And it also means that you can simply feed the new, if you want to change the chemistry in the model, you simply stick an extra reaction in, stick an extra species in. You simply tell the model you want one extra species, tell the model you want one extra reactant, and just give it to it. Off it goes. ASAP doesn't mind. Again, you get a little bit of chance to practice that in your tutorial, I think, in the course of this week. Relatively straightforward to change the chemistry. That's the advantage of using this kind of scheme. So, as I mentioned before, the chemical integration approach we tend to use is a backward Euler scheme with Newton-Raphson iteration. Okay. First step, what we do is we build the Jacobian. That's basically telling us about how the rates of change are dependent on each individual each individual tracer. So it's basically a large matrix of first-order partial derivatives, and that defines the system of coupled nonlinear equations that we're looking at, right? And then we have to solve it using the backward Euler approach. So we're looking at this equation here, and we've changed the notation a little bit here, unfortunately. But actually, this is very similar to what I showed you before for describing what the backward Euler scheme looked like. What we really want to do is solve for this term here, the concentration at the end of the time step minus the concentration at the beginning of the time step. That's the change in concentration over the time step, which is what we're actually after. Okay. What we have to do is solve for this here. And how do we do that? We use Gaussian elimination. Okay. Technically, this is actually LU factorization with partial pivoting. So what we're doing is we're arranging the rows in our Jacobian matrix to make a triangular matrix, okay? And then we're using back substitution. We're starting at the bottom, we're working up from row to row, taking one row away from the previous row to identify what the contribution of that one particular species is to the overall rates of change. This is actually how one would solve any kind of simultaneous equation using this kind of approach. And we speed it up in the model by using sparse matrix approach because quite a lot of these elements are zero. There are many different species in the atmosphere which don't directly affect each other. The effects are indirect. So lots of zeros in Jacobian, so we avoid doing the calculations for those. So we end up with a system that's rather more computationally efficient. Okay, so this allows us to solve this equation. All right. So the overall process, the full procedure, you start off at the beginning of the chemistry, building the Jacobian, building how the rates of change depend on the concentrations of each tracer. We make a first guess at what the concentrations at the end of the step should be. Okay, we tend to use an Euler method for that. Dead straightforward, very simple to apply. And we then calculate the rates of change using these concentrations. And then we calculate the residual term. Basically, what we're trying to do is we're trying to minimize this expression here. So we calculate what the difference in this concentration from the concentration at the start of the step is minus this rate of change times the time step length. All right? And then we check for convergence. Are we close to zero? Are we close enough to zero to be happy? All right? First time round, that's never going to be the case. Okay? So what we do, we rebuild the Jacobian. We solve this by Gaussian elimination to derive what the change in the concentration is over the time step. We then check for any problems that might occur. Okay, if there are problems with convergence and divergence, we might start seeing those at that point. And then we update the concentrations. And we go back to the beginning of the loop again with those concentrations, calculate the new rates of change, calculate our residual term here, and hopefully we're a bit closer to zero. Okay, and we go on, we iterate through this, go multiple times over this loop until we're close enough that we're happy we've converged. Okay, and at that point, we end up with the concentrations at the end of the time step. All right. There are numerical complications that might arise in certain situations. Maybe there's no convergence. Something's changing far too quickly for some particular reason. There's a very wide range of different chemical environments in the atmosphere. So if we're trying to use one chemistry scheme, one solver, to apply to all these different chemical environments, there are sometimes problems that occur. If it doesn't converge, typically what we try to do is retry but reduce the time step. Okay, so that's a little catch there that helps in problem situations. So a few characteristics of this scheme. Okay, the solution time is roughly linear in the number of entries in the Jacobian. Okay, generally, if you add an extra reaction, very often you might be adding one extra term in the Jacobian. Means the model won't slow down very much at all. Many schemes are proportional to the square of the number of species. So that's, of course, if you double the size of the chemistry, double the number of species involved, you might be making the chemistry 4 times slower. That's not the case in this particular for this particular integration scheme. So we've optimized things now, especially we've got sparse matrix approach. We actually end up with quite efficient. If you're adding just a few species or reactions, generally it doesn't affect the time very much at all. With a slight caveat that you might there are certain types of changes you could apply that might cause problems if the species are strongly coupled with species that are there already. And in most cases, our scheme converges in about 5 to 7 iterations or something, somewhere in that region. That's what we're looking for, reasonably fast convergence. The fewer steps we take, the more efficient the model is going to be, of course. And there are various little tricks here for improving convergence in problem situations. And often, again, we work on multiple grid cells at once. So we don't just work each one by one, each individual grid cell. We take a string of them and can do them all at the same time. That's generally computationally more efficient. So what do you need to know about all this in order to run UKCA? Very little, fortunately. We spent a long time getting the ASAD framework in place. So it's designed to be as black box as possible. You need to know how to add individual species. You need to know how to add chemistry. So the tutorials will give you an example of how to do that. But you shouldn't need to know very much about what's under the bonnet here. If there's a requirement for new species, view chemistry in ASAD, again, you go through some of this in the tutorial. The Newton-Raphson solver here tends to be very robust, but there are a couple of little issues to be concerned with. One is if the chemistry you add increases the stiffness of the system a lot. In other words, if you add some very short-lived species, then they may have problems with convergence. So in that situation, you should consider if these short-lived species are really needed or not, or whether you can get rid of them the way we did before, using steady-state assumption or family approach. Okay. And also, new steady-state species might require additional work too. Sometimes it's a little bit difficult to include those because they may need to be included in the Jacobian in some way. So there's a little bit of extra programming required for those. Make a little bit of a problem. But generally, we try to avoid adding any additional steady-state species. But these are two things which are not likely, you're not likely to meet unless you're making really major changes to the chemistry. If you're simply adding in, new biogenic hydrocarbons, for example, into the model, you won't have to worry about these kind of things at all. Okay, and it should be straightforward. The chemical solver there is really very robust, and it's hopefully it shouldn't fall over on you at any point. Touch wood. Okay, but if you're interested in numerical methods, this is still an area very much of scientific research. This is still one of the slowest parts of the entire model. Well, UKCA, even UKESM, one of the slowest parts is actually solving for the gas phase chemistry. So we're always looking for newer approaches, more original numerical approaches for reducing the computational requirements of atmospheric chemistry. So again, there's a lot of opportunity here if you're interested in numerical methods to think about applications within models like UKCA. I finished off with a few sources of extra information. Those other places you go to look at information on numerical methods. Okay, thank you.
Thank you.